Hey guys, Mike Calvino again here, and I thought I'd give a little explanation about some of the design of some of the windows and doors. In the Florida statutes, there are three different ways to meet the product approval system, and one of those is to show by comparative and rational analysis that the product meets the requirements of the code. Now what that means is doing statics calculations using properties of materials and connections and approved resources like the American Institute of Steel Construction manual, the National Design Specification from the American Wood Council, and ASTM specifications, things like that, to do calculations of all of the pieces. So in this case, let's say a glass wall, like a curtain wall system. Well, you know how expensive the aluminum systems are. There are many of them. And then there are also some things that you can't get, and they're all 2.5 inches wide. And for a lot of things you can do something thinner. We can do a 2-inch wide system to get it thinner. And in this case, I'm going to go through a Cypress design of a Cypress glass wall with a Cypress door in it, as opposed to a storefront system, which is usually a single member that either snaps together from two pieces and the glass sort of sits in the middle with a zip gasket kind of connection. So I call it my Cypress and glass curtain wall system, and in this case it didn't have to be impact resistant, but I went ahead and did it, made sure that it would meet the impact loading, one, so that I know I can do it in future projects, and the other reason is that down the line they could condition the space and have it become part of their living space instead of a sunroom, which does not have to be impact resistant as long as the inside walls are meet the code. So let me show you this little curtain wall system. So let me tell you a little bit about this little project, designing and building a little Cypress and glass curtain wall. You can see the section here. You got a backup member that's 2x, in this case a 2x6, and then you have just this notch, the notches for the glass that are just run on a dado blade on a table saw. Then you have the cap over here. The glass is set a bed of silicone here, and then another bed of silicone on the front, where the glass, the cap is put on with stainless steel screws. So here you can see the top connection. In this case, the main members are the verticals, and they are 2x8s. And I use number 14 stainless steel screws. In this case, they're 3.5 inches. And this is all calculated, the sizes are all calculated referencing the National Design Specification from the American Wood Council. So there you can see the stainless screws holding the cap on, which basically holds the glass in place. Let me tell you a little overall how this thing is working. The original house was done in the 50s, and there's no tie down for the roof, so I'm going to use this curtain wall system to kind of retrofit and at least tie the beams down. So there's a double 2x12 up there, and what I'm doing is using these number 14 screws to transfer the uplift into this frame. I got a 20 gauge sheet metal strap in the corner with 6 screws on each side, and so those number 14s transfer the load into the top mullion through the galvanized strap into the vertical, and then I use the vertical 2x8 as a tension member basically. to transfer that load down to the bottom corner where we have the same strap, 20 gauge galvanized sheet metal, the 6 screws on either side, and then in this case we're using a stainless steel wedge anchor that goes down through the sill mullion and into the concrete slab, and that gets us sort of a retrofit uplift resistance for this little system here. You can see I also can go through and figure out the door. The door is designed the same way, using simple statics calculations, limiting deflection based on the glass deflection of 3/4 inch. I can get my bottom clearance for the sweep, side clearances for the weather stripping, and so that's basically it, how this curtain wall system works. Next I'll go over the impact load calculations for the glass and also the wind load calculations real quick. Okay, so here we have the my glass sizing software is done in Grasshopper, so I can link it directly to the model, and I just grab elements from the model and use Grasshopper to get the section properties, thicknesses, areas, and all that stuff. And then I input the formulas, in this case defining the maximum stress allowable by ASTM E1300. And then we go over here to a 2-iteration calculation for the impact loading. First, what I have to do is run a simulation and get a deflection based on an impact from just the loading, and then we go back and run the impact again with the factored load for the velocity. And here you can see after we get the load, then we come back into Rhinoceros using a plugin called Scan and Solve, which is a finite element analysis program that runs right in Rhino. It uses the NURB surfaces to simulate loading conditions and calculate stresses and deflections. So you can see here how you define the edge or the support conditions over here, the restraints. Then this defines the load. I just make a surface in the center of the glass that's the size of the end of a 2x4, which is what the impact is, and then I put in here the factored load that we calculated in Grasshopper. Here you can see the second iteration using the impact factor to get the 801 pounds of lateral force. So then we run the simulation, and we get results like this. And there are a number of different results that we need to look at. The stresses are the critical. The max stress is the critical one that we need to look at. The other is deflection. Make sure we don't go over the maximum 3/4 inch deflection that's defined by ASTM E1300, and also the maximum calculated allowable stress for tempered glass, which we get from a formula that's defined in ASTM E1300. So here you can see the material properties that I input for the glass, and then down here we can see the maximum deflection of 0.208, and then down here we have the maximum principal stress at about 10,000 psi, which is less than the 13,500. And even if we go by the von Mises stress, which that's a little different stress that has to do with fracturing from deflection or bending. I mean, it's basically a molecular stress fracture in shear. But even that one is less than 13,500 psi. So we're good. And then here we go into let's make the curtain wall. So Got some roughs on Cypress here from the mill, and it's out in the mill. They just dry it out in the sun in a big yard, so it gets sand on it and everything. So I gotta clean all that off because it won't do my planer any favors when I run that through there. So a lot of boards, clean them off, stack them up, and of course you gotta have my Mountain Dew. So this is the next step. Alright, so here we are. Ran all the stuff through the planer. Now here is the door, fabricating the door. It's got side rails. The rails are basically a 2x4 that's split. So it's a square profile, about 1 7/8 inches square. Closer to 1 3/4 inches probably. And then the horizontals, the top and bottom, are again the same square profile, and then the intermediate, the main intermediate, is at 33 inches. It aligns with the horizontal mullion in the curtain wall, and that one is where the knob is. Now that one's a 2x6, and that gives us a little bit of planar resistance in the plane of the door, and then the one for the deadbolt is a 2x4, and then everything is notched except the glass in there, and the hardware is put on first. Here we go. I got to catch up to the slides showing the frames. You saw the straps on the corners, and here are the frames set in the openings. And this is the main frame in the front that's just being put together. So it went in pretty well, and I just need to seal up the corners and install the glass. So we'll see you on the next time.